Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 21, and we are going to continue with our discussion on extension torsion inflation in cylinder. Okay. So, at the end of the last class we had derived the reduced form of equations which we have to solve to obtain the displacement. Okay. So, the equations were del sigma r r over del r plus sigma r r minus sigma theta theta over r equal to 0 and del sigma z z over del z equal to 0. Okay. So, these were the equations. So, let us try to solve them one by one. So, if we take the second equation, so we know that sigma z z, for example, that is lambda times u r prime plus u r by r plus u z prime, that is a trace of the strain matrix, plus 2 mu epsilon z z, right. So, u z prime. So, we could also write this as lambda plus 2 mu u z prime plus lambda times u r prime plus u r by r. Okay. But because del sigma z z by del z is 0, that means sigma z z has no dependence on z, right. So, this means sigma z z does not depend on z. So, sigma z z, we also know it does not depend on theta. So, it can only depend on r, the radial coordinate. So, this means this expression for sigma z z is equal to some function f of r. Okay. But now, let us look at the left hand side and right hand side here. This thing here depends on r, whereas this thing over here depends on z, because u z is only a function of z. So, u z prime will also be just a function of z, not of r. So, there are two things on the left hand side, one depending on z, one depending on r, and the sum is equal to something which only depends on r. So, this tells us that on the left hand side the dependence on z is actually not there. So, this tells us that u z prime should actually be a constant. There has to be no dependence on z, because if there is some dependence on z on left hand side, then right hand side would also have to be a function of z. Okay. So, u z prime is some constant, and as we know u z prime is axial strain del u z by del z. So, we will call it by epsilon, okay, the axial strain. A constant. So, along the axis of the cylinder, wherever you go, the axial strain is a constant. It neither depends on r. So, for a given cross section, every point on the cross section has got same axial strain, there is no dependence on r, and two different cross sections also, which have two different z, also have same axial strain epsilon. So, in the cylinder every point of the cylinder has got the same axial strain epsilon. Okay. All right, what more can we say now? So, this is coming from the second equation. Let us look at the first equation, what do we get from there? So, we have del sigma r r over del r plus sigma r r minus sigma theta theta over r equal to 0. So, let us plug in the formula for sigma r r and sigma theta theta. So, we know that sigma r r, for example, is lambda times u r prime plus u r by r plus epsilon, because u z prime is epsilon, plus 2 mu u r prime. Likewise, sigma theta theta is lambda times u r prime plus u r by r plus epsilon plus 2 mu u r by r, right. So, what is sigma r r minus sigma theta theta, because we need that in this equation here. So, that is simply 2 mu into u r prime minus u r by r, correct. So, let us put that in this equation. So, the first one is del sigma r r by del r. So, from the expression it is going to become lambda times u r prime plus u r by r whole prime plus lambda into epsilon prime, but because epsilon is a constant, epsilon prime becomes 0. So, we have then plus 2 mu u r double prime plus sigma r r minus sigma theta theta by r, which is 2 mu into u r prime minus u r over r, and this is equal to 0. Okay. But we have to see that this whole thing actually is 2 mu u r prime plus u r by r whole prime. So, when you do the derivative, you will see that these two become the same, okay, because you see the first one goes here and the second one, when you apply product rule of differentiation, gives you the two terms here. Okay. So, finally, this means we have lambda plus 2 mu into u r prime plus u r by r whole prime equal to 0. Okay. Well, so that means u r prime plus u r by r is actually a constant c, all right. You see the u r prime is epsilon r r and u r by r is epsilon theta theta. So, this also tells us that the radial strain plus the hoop strain is equal to a constant. Okay. Anyway, let us proceed further. This then becomes 1 over r u r into r whole prime. So, can you see this? When you do the differentiation, you will exactly get what is there in the top, okay, and this is equal to a constant c. So, that means u r into r whole prime is equal to c into r. So, u r into r then becomes c into r square by 2 plus another constant d, and finally, u r then becomes c into r by 2 plus d by r. Okay, so we have gotten the formula for u r already, but in terms of the constant c and d. Okay. Coming back to our equation, let us try to also see what is sigma r r plus sigma theta theta. So, we have the expression for sigma r r and sigma theta theta here, right. Now, let us add them together, and what do we get? So, when we add them together, we simply get 2 times lambda plus mu into u r prime plus u r by r plus 2 lambda times epsilon. Okay. But then we know that u r prime plus u r by r is a constant. So, this also implies this is equal to 2 times lambda plus mu into this constant c plus 2 times lambda into epsilon. So, you see on the right hand side everything is a constant. So, it also tells us that the sum of the radial stress and hoop stress is equal to constant. So, radial stress will vary with r. So, as you go along the thickness of the hollow cylinder, the radial stress is going to vary. Likewise, the hoop stress is also going to vary, but their sum will be a constant. So, that is very interesting. Okay. All right, but we can use this to solve the equation in a simpler way. So, let us come back to our equation. So, that is del sigma r r over del r plus sigma r r minus sigma theta theta over r equal to 0, right. So, we could also write this as del sigma r r over del r plus 2 times sigma r r over r minus sigma r r plus sigma theta theta over r. So, you see we add one sigma r r by r and we also subtract one sigma r r by r, and this is equal to 0. But we know that sigma r r plus sigma theta theta is a constant. So, let us call that constant as being equal to a. So, that means finally, we have del sigma r r over del r plus 2 times sigma r r by r, and that is equal to this constant a divided by r, correct. Now, are you familiar with solving this kind of equation? So, it has only sigma r r which depends on only r, right. So, it is basically a differential equation with variable coefficient, because you have 2 by r, but you might recall the integrating factor formula. So, we can use that also here to solve this differential equation. The other way is on the left hand side we have 2 terms, we can combine them together. You see this could also be written as 1 over r square of d by dr into sigma r r times r square. So, when you take the derivative you will get exactly the 2 terms. Okay. So, this is equal to a by r. All right, so we are almost there. So, this means sigma r r into r square whole prime is equal to a times r, correct, which further means that sigma r r into r square is equal to a into r square by 2 plus b, and finally, then sigma r r is equal to a by 2 plus b over r square. Okay. So, we got the formula for sigma r r in terms of two constants. Whenever you solve a differential equation, you get constants, but to obtain those constants you have to apply a boundary condition, right. And luckily our deformation problem, which has got those equations, also comes with the boundary condition, right. So, for example, our own problem, we have this cylinder and then we know that internally we are applying this pressure correct. So, we are applying this pressure internally. So, that is the external traction that is being applied, and on the outer surface we are not applying anything. So, what can we say about the stress components on the outer surface and on the inner surface? So, outer surface is characterized by outer radius r 2, let us say, and the inner surface is r 1. Okay. So, we are basically saying that the inner one is r 1 and the outer one is r 2. So, what can we say about sigma r r at r 1 on the inner radius? You see, on the inner radius sigma r r, so that is a negative r plane, is not it, because its outward normal is pointing towards the axis of the cylinder. So, in the negative E r direction. So, the stress components or the traction components on that surface will be pointing in the negative direction. So, sigma r r will be pointing in the negative E r direction. Likewise, tau theta r and tau z r, they will be pointing in the negative directions. But anyway, you see, we are applying pressure which is in the radial direction. So, the external traction that is being applied is in the radial direction. So, you can recall that whatever you apply externally on the surface of the body, the internal traction becomes equal to what you apply, right. So, that means the stress sigma into the surface normal, that is equal to what you apply. So, T applied for the inner surface. What is the surface normal? So, that is negative E r, right. So, in the E r E theta E z coordinate system, it is going to be minus 1 0 0. So, when we write this in E r E theta E z coordinate system, we have this stress matrix multiplied with minus 1 0 0, correct, and this is equal to the traction that is being applied, and what we are applying is pressure in the positive E r direction. So, that traction will become P 0 0, is not it? And so, from here you get that sigma r r with a minus sign, then minus tau theta r and minus tau z r, the first column of the stress matrix into minus sign. So, that is equal to P 0 0, right, which then means that sigma r r at r 1 is equal to minus of P, tau theta r at r 1 is equal to tau z r at r 1 and that is equal to 0. So, these are the boundary conditions. Likewise, on the outer surface, because you are not applying anything and the outer surface normal is E r again 1 0 0. So, the first column of the stress matrix will simply be 0, correct. And when you talk in terms of sigma r r, so sigma r r at r 2 then becomes 0, right. So, sigma r r at r 2 is also equal to 0, because the outer surface is traction free. Okay. All right. So, this is going to be useful for solving the equation here. See, we have to say that sigma r r at r 1 is equal to minus p and sigma r r at r 2 is equal to 0. Okay. Now, our equation for sigma r r is a plus b by r square. So, this implies a plus b by r 1 square is equal to minus p and a plus b by r 2 square is equal to 0. Okay. And finally, when we solve these two, we will simply get that a is equal to 2 times p into r 1 square over r 2 square minus r 1 square, and b would be equal to minus p into r 1 square r 2 square divided by r 2 square minus r 1 square. Okay. So, for a positive pressure internally, then this is greater than 0 and this is less than 0. If your pressure P, what you apply internally is positive. Okay. Sorry, this is A by 2, isn't it? So, that is A by 2, and when you solve it, you get A equal to this and B equal to this, all right. Now, that is sigma r r and sigma theta theta, because we know that the sum of the two is equal to the constant A. So, sigma theta theta would then be A by 2 minus B over r square. Okay. And if we want to, let us say, draw the variation in sigma r r and sigma theta theta. So, suppose this is r, and then on the y axis we have sigma r r and sigma theta theta. You see, from the formula, what happens as r goes to infinity? As r goes to infinity, sigma r r becomes A by 2 and sigma theta theta becomes A by 2. But because it is a cylinder, the r is between r 1 and r 2, right. So, we will have some r 1 and some r 2, and the stress has to vary in this domain. But the formula is such that as r goes to infinity, both of them have to approach A by 2, and you see A is positive here. So, A by 2 will be a positive number. So, we can think of a line which is at A by 2, okay, and both the curves for sigma r and sigma theta theta have to approach this line as r goes to infinity. Now, we know that sigma r r at r 1, that is equal to minus of p from boundary condition, right. So, there will be some point where it will be minus of p. and then your sigma r r starts from minus of p, and then your sigma r r starts from minus of p, and at r 2 it has to become equal to 0. So, it is going to be something like this, and outside this it is going to approach this a by 2 line asymptotically. Okay. And your sigma theta theta will be the mirror image of sigma r r about the a by 2 line, because both of them when you add has to be a constant. So, sigma theta theta is going to be the mirror image of sigma r r about a by 2. So, whatever is this distance here, you go by the same distance upward, okay, and then you get the starting point of sigma theta theta. Okay. Likewise, even for this point here, it is somewhere over here, and you add them, and after this it has to reach a by 2 asymptotically. Okay. So, basically this is how sigma theta theta. So, I will just make it more thick, and sigma r r vary within the cylinder. And you also see here the coefficients A and B, it depends on the pressure P. If the pressure P is 0, so that means if you do not apply anything internally, then sigma r r and sigma theta theta are 0. So, even if you are stretching the bar or applying twisting moment, they do not affect your sigma r r and sigma theta theta. You see, right now we are solving it when all three were present. Nowhere we said that the twisting moment is 0 or the axial force is 0. From the derivation it simply comes out that sigma r r only depends on pressure P, the internally applied pressure. So, we can make a comment here, or we can make a remark that sigma r r and sigma theta theta are non-zero only if pressure P is acting. Okay. If P equals 0, then sigma r r equal to sigma theta theta is equal to 0, even if axial force and twisting moment or torque are present. All right. And it is also kind of intuitive, because suppose you are just stretching the bar and you are not applying anything internally or externally. So, it is free to relax, the cross section is free to relax, and therefore, the radial stress should be 0, not just on the boundary, but also within. Of course, if it is not a circular cylinder, if the cross section has got an irregular shape, then it is not necessary. Even when you stretch, you can get some sigma r r and sigma theta theta, but with circular cylinder, sigma r r and sigma theta theta becomes 0 if there is no pressure. Okay? Very good. All right. So, this was about sigma r r and sigma theta theta, but we still have to get the displacements, right. So, let us try to find out the displacement, how to get the displacement, how to get displacements. All right. So, we remember or we can recall that u r turned out to be c by 2 r plus d over r. And what was c equal to? Can you recall that sigma r r plus sigma theta theta was equal to 2 times lambda plus mu into c plus 2 lambda epsilon, and we called it as A, right. And then we also just found out what is A equal to, you see here. So, we can write here that this is equal to 2 into p into r 1 square over r 2 square minus r 1 square. So, this implies that the constant c is equal to minus of lambda over lambda plus mu times epsilon, right, plus p by lambda plus mu into r 1 square over r 2 square minus r 1 square. All right. So, that is c, and now we have to get also d. So, how to get d? So, to do that, maybe let us write down the expression for sigma r r. So, sigma r r is, now we know it is lambda times u r prime plus u r by r plus epsilon plus 2 mu into u r prime, and this is then lambda times c plus epsilon plus 2 mu, and then u r prime we can write from the expression for u r here. So, this becomes c by 2 minus d by r square, right. So, this is finally lambda plus mu into c plus lambda epsilon minus 2 mu into d by r square. Okay, so, that is the expression for sigma r r, and we also said that it is a plus b by r square, correct. So, from here we can find out what should be d. So, when we relate these two, we can see that d is actually minus b over 2 mu, is not it? And b we have just found out right here. So, d becomes p times r 1 square into r 2 square over r 2 square minus r 1 square by 2 mu. Okay. So, d is now a positive value greater than 0. All right. So, with this, what can we now say about u finally? So, we have c as well as d here. So, that is your c. So, u r is then equal to c by 2 r plus d by r. So, c by 2 r would be minus lambda over 2 times lambda plus mu into epsilon plus p over 2 times lambda plus mu into r 1 square over r 2 square minus r 1 square, okay, plus d by r, is not it, c by 2 r plus d by r. So, when you do plus d by r, we get p by 2 mu r into r 1 square r 2 square over r 2 square minus r 1 square. okay, and the first two terms we know has to be multiplied with little r, c by 2 into r, all right. So, that is the formula for the radial displacement. And again, can you see what happens if pressure is equal to 0? So, if P is equal to 0, then u r is simply minus lambda over 2 times lambda plus mu times epsilon into your r. Okay. And you know, when you relate lambda and mu with Young's modulus, shear modulus and the Poisson's ratio, it turns out this lambda over 2 times lambda plus mu is actually the Poisson's ratio. So, this is then minus nu the Poisson's ratio times epsilon times r. So, that is your u r. So, can you now see what is epsilon r r? So, epsilon r r is simply u r prime, and that becomes minus mu into epsilon. And is not that obvious? From the Poisson's effect, when you apply axial strain epsilon, then the radial strain in the lateral direction is minus of the Poisson's ratio times epsilon, right. But of course, if pressure is also present, we have the extra terms also proportional to pressure, all right. So, this is u r, and what is u z? So, u z we have already figured out. We said that u z prime is equal to this epsilon. So, that means u z is simply epsilon times z, where epsilon is the axial strain, okay, and u theta we have already gotten it, that is omega by L into r into z. So, that is u theta. And what are still remaining now? You see, we still do not know what is epsilon and what is omega, we still do not know these two. What we know is that we have applied axial force F and twisting moment m. So, perhaps from these two information we will be able to obtain epsilon and omega. So, for example, what would be the torque T? So, suppose we have this cross section, so this is the cross section, it is the z plane, and on this plane we have sigma z z acting as well as tau theta z. So, at any point tau theta z would be in the theta direction. Correct. So, what will be torque due to this traction? Let us say if there is some traction T acting on this cross section, then what is the moment due to the traction? So, the moment vector m, so we have to find this, but we postpone it for now. We first calculate the moment vector m. So, moment due to traction about the origin, okay, let us say about O. So, that is going to be equal to integration over the cross section, is not it, of the arm of the traction, which is little r E r, cross product the traction T at r comma theta times d A, the area, small area, which would be r dr d theta, right. So, that is the moment, all right. So, this is then integration over omega r E r cross product the traction. Now, on this z plane what are the tractions acting? We have sigma zz in the Ez direction, and we also have tau theta z in E theta direction, and we know there is no tau r z. So, that is the traction into r dr d theta, or we also know this is dA. Okay. So, the torque T, what will be the torque T equal to? So, torque is the moment along the axis. So, that is simply moment m dotted with E z, correct. So, here it then becomes integration over omega r E r cross product this thing and then the whole thing has to be dotted with E z into dA. Okay. But you see E r cross E z will be perpendicular to E z, and when you dot with E z it becomes 0. So, this one does not contribute here. So, this implies that the torque T is equal to integration over omega, and what is E r cross E theta? E r cross E theta is simply E z and dot with E z, you get 1. So, torque T then becomes r into tau theta z into dA. So, that is the torque. So, torque comes due to tau theta z, and we can now plug in the formula for tau theta z, is not it? So, this becomes integration over omega of a small r into g times gamma theta z dA. And you can recall from the previous class that gamma theta z was equal to omega times little r by L. Okay. So, we can put this here. So, this becomes integration over omega of g into omega by L times r square dA. All right. So, I think we should make some change in notation. The cross section, let us denote it by omega naught. Okay. Because we are also denoting the rotation by omega, no. All right. Now, what is this quantity here? Integration over the cross section r square dA. What is that? Is not that the polar moment of area? So, this is this thing inside the bracket, that is called the polar moment of area, and it has got a name also, it is denoted by J. Okay. So, this finally becomes G j times omega over L. So, the torque T is equal to G j times omega over L. So, we got a very interesting formula. So, if torque T is known, you can compute omega by saying that this is equal to T L by G j. So, the end to end rotation omega is T L by G j, where T is the torque applied. And if you know the end to end rotation omega, then torque T you can get from this formula here. Okay. So, that is how we get omega. Okay, we still have to get epsilon, right, and I guess it should be related to the axial force applied, is not it. So, let us try to get epsilon in terms of the axial force. So, we again have the cross section, and the axial force is the force in the axial direction, So, it should simply be integration of sigma z z, is not it. So, the force F is the integration over the cross section of sigma z z times d A. But what is sigma z z? So, sigma z z, we know it is lambda times u r prime plus u r by r plus u z prime plus 2 mu into u z prime, right. And we know that u r prime plus u r by r is a constant, which we denoted by c. So, this becomes lambda times c plus lambda plus 2 mu into u z prime, which is also equal to epsilon. So, that is lambda times c plus lambda plus 2 mu into epsilon. So, we can simply write it here, and it becomes integration over omega naught lambda c plus lambda plus 2 mu into epsilon. So, this is a constant, right. So, it simply comes out of the integration, and this becomes lambda c into the cross sectional area A plus lambda plus 2 mu times epsilon into the cross sectional area A, all right. So, that is how we can relate force with epsilon, because C we already know it, we had the formula for C. So, we can put it here, and the only unknown would be epsilon. So, you can then also obtain the axial strain in terms of the force applied. Okay. And there is of course, again an interesting case, what if there is no pressure? So, what if there is no pressure acting? So, in that case we know that sigma r r is equal to sigma theta theta is equal to 0, correct. And then we can use the stress strain relationship, the 3D Hooke's law, which says that epsilon z z is equal to 1 over E into sigma z z minus nu times sigma r r plus sigma theta theta, correct. So, from here, because these two are 0, we get that sigma z z is equal to E times epsilon z z, which is equal to epsilon. So, the axial force F, which is simply the integration over the cross section of sigma z z d A, it then becomes E A times epsilon, correct. Axial force F relating with the axial strain, and the constant is E A, all right. So, let me write it in a box. So, we figured out that F axial force is equal to E A into epsilon, and the torque T is equal to G J into omega by L, where this is the axial strain and this number here, that is the twist, okay. And on the left hand side this is axial force and this is torque. So, torque is related to twist and axial force is related to axial strain. And what is the constant that relates? They are E A and G J, and they have got a name also. So, this is called stretching stiffness of a cylinder or of a bar. okay, whereas this thing is called twisting stiffness or torsional stiffness. All right. We also see that the axial strain epsilon is constant in the cross section. This twist omega by L is also a constant number, but what about the shear strain that generates this torque, or what about the shear stress tau theta z? So, the question is, how do shear stress tau theta z and the shear strain gamma theta z vary in the cross section? So, this is again very interesting. So, we just saw that gamma theta z is equal to omega over L times r, correct, whereas tau theta z is then g times gamma theta z, and that becomes g into omega over L times r. So, you see that both of them vary linearly with the radius. So, whenever you twist a bar or twist a cylinder, then in the cross section, as you go outward, the shear strain as well as the shear stress, they vary linearly. So, you can draw a graph like this. For shear strain, and likewise also for shear stress. Okay. Very interesting thing is, think of a composite cylinder, so which is formed by two different materials. So, let us think of a composite cylinder. If the cross section is like this, and suppose the inner part, so that is aluminum, whereas the outer part, so that is steel, and suppose that they are glued together tightly, and to this composite cylinder we twist the cylinder. So, when you twist this cylinder, the cross section as a whole is going to rotate. Okay. So, the shear strain gamma theta z would still be omega over L times the radius. So, if I draw gamma theta z versus r, it will simply be straight line. But what about tau theta z? Tau theta z, we know it is g times gamma theta z. So, in the steel portion, we will have to take the shear modulus of steel, and in the aluminum we will have to take the shear modulus of aluminum. So, this is for gamma theta z, which varies linearly, but for the tau theta z, it is going to be different. So, it first varies linearly with one linear graph within the aluminum. So, this is the aluminum domain, but for the steel domain it has to have a different slope, because the g is different, and there will be a jump. There will be a jump in shear stress. across the interface. But there is no jump in shear strain, no jump in shear strain, and the reason is simply because steel and aluminum both are acting as a single body, because it is rigidly attached. No? So, when it deforms as a single body, but the stress that gets induced or the stress that generates in the body will depend on the material property. Steel has got different material property, aluminum has got different material property. So, the stress generated will be different, but the strains will be like a single body. Therefore, there is no discontinuity in strain, but there will be discontinuity in stress tau theta z. All right. So, I will end the lecture here and we continue in the next class. Okay. Thank you.